this is Lynn, the chemistry tutor. In this video, I'm going to talk about the acid-base strengths, Ka, Kb, and Kw. We talked about earlier that acid and base, according to the Brownstein-Lowry definition, acid are proton donors and base are proton acceptors. So a strong acid is defined as an acid that dissociates completely when dissolved in water, which means when it reacts with water, water will act as a base, a proton acceptor, and 100% all the acid will become H3O plus and Cl minus. According to the Hampton book, the Chem 12 workbook, that's used in mostly BC, Vancouver area, there are 6 strong acids: perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. And actually there are more to this list, but those are the most common 6 strong acids that we will see in most of the questions. And the weak acid, on the other hand, doesn't behave like the strong acid. So the weak acid, they only dissociate partially when they dissolve in water, which means only a small fraction of it dissociates into its conjugate base and the hydronium ion. So as a result, this is a equilibrium situation. Because it's an equilibrium, so we can write out the expression for its KEQ. Because in this case it's an acid, so the particular KEQ is called Ka. Ka would be the product of the product over the top and over the reactant as the denominator. And because it's a Ka, it's producing H3O plus. A larger Ka indicates that at equilibrium you have more H3O plus produced. So a larger Ka indicates that weak acid is relatively strong. And the stronger the acid, the weaker its conjugate base would be, because the more likely the acid is producing H3O plus, the less likely the base can accept that proton and go back to the acid. And so this is about strong acid and weak acid. Similarly, strong base and weak base are behaving the same way. So a strong base is a base that can give, that's a proton acceptor. So when a strong base dissolves in water, all of the base will dissociate completely, and then water will become OH minus. This is something that's confusing sometimes, because when we have strong base, most of our strong base are metal hydroxide. So when we are writing metal hydroxide dissolving in water, we actually don't put in water, so we just write NaOH. One way produces Na plus and OH minus. If it's a metal hydroxide dissolving in water, we don't have to put the water in there, because the metal hydroxide itself is producing the OH minus. But there are 2 additional strong base apart from the metal hydroxide, is the oxide and the amide. So oxide is a strong base, so when oxide is reacting with water, then it's one-way arrow because it's 100%, and the O2 minus will be a proton acceptor, so it becomes OH minus. At the same time, water is a proton donor, it also becomes OH minus. So as a result, when OH minus O2 minus behave like a base, you actually produce 2 OH minus in the end. A weak base are base that can only dissociate partially. Again, weak base will react with water and then produce OH minus in an equilibrium. So similarly, the Kb can be defined like Ha times OH minus over the base at the denominator. So if an acid is relatively strong, then its conjugate base will be relatively weaker. Lastly, we're going to talk about the self-ionization of water. So water is both an acid and a base. So we call this type of things amphiprotic. Amphiprotic means something that can be both an acid or a base. So when water it's alone, it can behave like both an acid and base. So as a result, even in pure water, we have H3O plus and OH minus. So the equilibrium constant for this equilibrium is called Kw. So Kw is because on the left hand side of the equilibrium we have two liquids. We don't have to include pure solid and pure liquid in our KEQ expressions. So in this case, the Kw only equals to hydronium ion concentration times OH minus concentration. At 25 degrees, Kw equals to 1.0 times 10 to the power of negative 14. But something to keep in mind, Kw, Ka, and Kb, they are all technically equilibrium constant. Their values don't change unless there is a temperature change. When temperature changes, Ka, Kb, and Kw will change. And most of the time, since the ionization process is endothermic, so when temperature increases, the K will also increase. In the case of Kw, at 25 degrees, Kw is 1 times 10 to the power of negative 14, but as temperature increases, Kw will increase. Also, if you plug in the Ka and Kb for a pair of conjugate, you would probably be able to figure out that Ka times Kb equals Kw, which means for a pair of conjugate acid and base, the Ka of the conjugate acid times the Kb of the conjugate base should equal to Kw. In the end, I want to talk about something called the leveling effect of water. The leveling effect of water means like if I have a strong acid, like say HCl and HBr or HI, so all the strong acid, no matter how strong the acid is, all the acid can do is to give its proton to water. So as a result, in any aqueous solution, no matter how strong your acid is, the strongest acid is just hydronium ion. And similarly, when I have a strong base, the bases are proton acceptors. All they can do is to extract the hydrogen from water and making water into OH minus. So the strongest base in water is OH minus. Thank you very much for watching this small video. Hope it's helpful to you. See you soon. Bye.